Hello, dear listeners, and welcome to Sleepy Science Teller. Tonight, we're drifting into the quiet vastness of the universe to explore one of the most mysterious and terrifying objects ever known, a star so powerful that if it turned its gaze toward us, it could erase all life in an instant. But don't worry, you're safe here, in this calm corner of the cosmos. We're simply going to wonder together. Before we begin, tell me in the comments, where in the world are you watching from and what time is it? Right now, I love knowing where all of you peaceful dreamers are listening from. And if you enjoy drifting into science just before sleep, please gently tap the like button and subscribe so you can join me again under the quiet stars. Imagine yourself lying quietly beneath a dark sky. 1,000 tiny lights shimmer above you, each one a sun millions or billions of miles away, each one a furnace of unimaginable heat. And deep inside every glowing point lies a story of creation, destruction, and balance. Stars are the engines of the universe. They're the reason atoms fuse, the reason galaxies glow, and the reason life, even here on Earth, can exist at all. Every breath of air, every drop of water, every grain of soil owes its origin to a star. But like all things that give life, they also carry within them the quiet potential for destruction. The same energy that warms and nurtures can also scorch, vaporize, and erase. Our own sun is a gentle giant by cosmic standards. It burns steadily, calmly, for billions of years. Its warmth reaches Earth just right. Not too much, not too little. A delicate balance that sustains oceans, forests, and you. But if our sun were just a little more massive, its power would grow not gently, but violently. A star only twice the size of the sun burns through its fuel nearly 10 times faster. It shines brighter, but dies younger, collapsing in a final burst that can outshine an entire galaxy. This is the first clue to what makes a star dangerous. It is mass. A star's mass decides everything. How it lives, how it dies, and how much chaos it releases into the universe when that final moment comes. Massive stars live brief, brilliant lives. They burn their hydrogen fuel at a furious rate, their cores fusing elements heavier and heavier until the balance breaks. When gravity can no longer be held back by fusion's outward push, the star implodes, collapsing into itself, and then rebounds in a violent explosion known as a supernova. These explosions scatter new elements into space: carbon, oxygen, iron, the building blocks of planets and people. But they also release radiation, energy, shock waves that can sterilize entire regions of the cosmos. In their brilliance lies danger. In their death lies creation. That is the paradox of stars. When we look at a star through a telescope, we see serenity, a calm point of light, fixed in the night. But inside, there is chaos beyond imagining. The temperature in a star's core can reach millions, even billions of degrees. Atoms move so fast, they fuse together, releasing bursts of light and heat. This process, called nuclear fusion, is what keeps a star alive. But the more massive the star, the more violently that fusion occurs. And that violence builds tension. For millions of years, a star fights a constant war between two forces: gravity, which tries to pull everything inward, and pressure, which pushes outward from the heat of fusion. The moment one wins, the star's fate is sealed. If gravity wins, the star collapses. Its core compresses into something unimaginably dense, sometimes forming a neutron star, and in extreme cases, a black hole. In that collapse, the star releases energy, not gradually, but suddenly, explosively, catastrophically. In one blinding instant, it can radiate more energy than the sun will produce over its entire 10 billion year lifetime. Such a burst of energy is enough to vaporize any planet nearby, to strip atmospheres from worlds light years away, and to flood the galaxy with lethal radiation. Astronomers have seen these cataclysmic deaths through distant telescopes. They observe faint pinpricks of light, suddenly bloom, then fade over days or weeks. Each one marks the end of the star and the beginning of countless new journeys for the matter it leaves behind. To understand why stars can be so dangerous, you have to understand scale. Our sun is already enormous. About 1 million Earths could fit inside it, but there are stars so large. They make our sun look like a tiny spark beside a bonfire. Take, for instance, the red supergiant Betelgeuse. If it replaced our sun, its outer layers would extend beyond the orbit of Jupiter. Its life is nearing its end, and one day, it too will explode as a supernova. Even from 600 light years away, it will shine as bright as the full moon, and yet that's still safe. At that distance, its deadly energy will pass us by harmlessly. But imagine a star like Betelgeuse, only a few light years away. The shock wave, the radiation, could strip Earth's atmosphere bare. It would be as if our skies were torn away in an instant. So what makes a star dangerous is not only its mass, but its proximity and its stage in life. The closer we are, and the nearer it is to death, the more perilous it becomes. Yet, as frightening as that sounds, there's a quiet comfort in how space is arranged. The universe is vast, and most of the truly dangerous stars live far, far away from us. Our solar system floats in a gentle, calm arm of the Milky Way, a region free from dense star clusters and violent explosions. It's almost as if nature chose a quiet neighborhood for life to bloom. This calmness is rare. The core of our galaxy is a wild, radiant storm, packed with massive stars, black holes, and deadly bursts of energy. But here in our quiet spiral arm, space is serene. We orbit safely, bathed in the soft warmth of a stable star. Our sun may one day grow old, expanding into a red giant, and then shedding its outer layers gently, leaving behind a white dwarf, a glowing ember of what it once was. No explosion, no deadly burst, just a slow fading into cosmic quiet. It's comforting to know that not all stars end in violence. Some simply grow tired and rest. But for those that do die in fury, their danger reminds us of something profound. Every violent end in the universe creates the possibility of new beginnings. The iron in your blood was forged in the heart of such a dying star. The calcium in your bones, the oxygen you breathe, the gold on your finger, all were born from stellar destruction. So even the most dangerous star plays a role in something beautiful. A star is dangerous because it is powerful, and it is powerful because it gives and it takes in equal measure. As you imagine those distant suns burning silently in the velvet dark, remember that danger and beauty often travel together. In the universe, that is what makes a star dangerous, and magnificent all at once. Imagine you're floating through the endless night of space, a place so still, so silent, that even light seems hesitant to move. For millions of years, the darkness remains untouched. Then suddenly, a blinding flash cuts across the void, so powerful, so radiant, that for a brief, fleeting instant, it outshines every other star in the universe. This is a gamma ray burst. It is the single most violent and energetic event known to science, and yet it happens in silence, so far away that even its echo barely reaches us. Astronomers first discovered these mysterious bursts by accident. In the late 1960s, during the height of the Cold War, American satellites called Vela were watching Earth's atmosphere, looking for secret nuclear explosions. But instead of human tests, they began detecting strange flashes of radiation coming from deep space. These weren't man-made. They were cosmic. They were gamma rays, the most energetic form of light in existence. Light so powerful that a single photon could pass through several feet of solid metal. For decades, scientists didn't know what caused them. They called them simply GRBs, gamma ray bursts. Each one lasted just seconds, yet released more energy than our sun will emit in its entire 10 billion year lifetime. What could do that? What kind of cosmic engine could burn with such unimaginable intensity and then vanish almost as quickly as it appeared? To understand that, we have to look into the heart of dying stars and witness how some of them end not with a whisper, but with a cosmic scream. When a massive star reaches the end of its life, its core runs out of fuel. Fusion, the process that kept it alive, comes to a stop. For millions of years, the star has balanced perfectly, gravity pulling inward, heat and radiation pushing outward. But when that delicate balance breaks, gravity wins. The core collapses in an instant. The outer layers fall inward, and the entire star implodes, crushed under its own weight. Inside that chaos, something extraordinary happens. The core becomes so dense that even atoms themselves are squeezed out of existence. Protons and electrons merge, forming neutrons. A neutron star is born, a sphere no larger than a city, but heavier than our sun. If the collapsing star is even more massive, the collapse continues, beyond the point of no return. A black hole is created, and it's in these moments when the collapsing core and still falling outer layers interact that a gamma ray burst can form. Two narrow jets of energy are blasted out from the poles of the collapsing star. They move at nearly the speed of light and carry unimaginable energy. They pierce through the dying star's outer layers and erupt into space as beams of deadly gamma radiation. Each jet is like a cosmic sword, thin, focused, and unstoppable. And for a few seconds, the universe shines brighter than it ever will again in that spot. These are called long-duration gamma ray bursts. They last anywhere from 2 seconds to several minutes, and are almost always born from the death of a massive star, a hypernova. There are also short-duration bursts, lasting less than 2 seconds. These come not from collapsing stars, but from something even more exotic, the collision of two neutron stars, or sometimes a neutron star merging with a black hole. When these ultra-dense remnants collide, they send ripples through space-time itself, gravitational waves, and release a burst of gamma rays that can be detected across billions of light years. In both cases, whether born from collapse or collision, the result is the same: a flash of deadly beauty, so bright, so intense, that for a few heartbeats, it outshines everything else in the universe. And then it's gone. A blink, a whisper, a cosmic exhale. When you look up at the night sky, you're seeing the light of stars that has traveled for centuries, millennia, even billions of years to reach you. Some of that light left its home before Earth even existed. So when astronomers detect a gamma ray burst, they are witnessing an event that may have happened long before our planet was born. That's one of the most humbling truths of all. We are observing the past through the faintest whispers of light. Most gamma ray bursts occur in galaxies far, far away, billions of light years distant. That means their deadly beams are no threat to us. By the time they reach our galaxy, their energy is diffused, their light softened by time. Still, scientists have wondered, could a gamma ray burst ever strike Earth? And the answer is yes, but it's rare. In fact, some researchers believe it may have happened before. About 440 million years ago, long before the age of dinosaurs, Earth went through a mysterious mass extinction, known as the Ordovician Silurian extinction. Many sea creatures vanished almost overnight. Some scientists suggest that a nearby gamma ray burst might have been the cause. If true, it would have been a burst perhaps 6,000 light years away, close enough for its radiation to strip away part of the ozone layer, allowing ultraviolet light from the sun to reach the oceans and disrupt life's delicate balance. Though we can't be certain, it's a sobering thought that something so distant could reach across time and space to touch a single world. But remember, such events are exceedingly rare. Our position in the Milky Way is a safe haven. We are tucked in a quiet arm of our galaxy, far from the dense, chaotic regions where massive stars are born and die. It's as if the universe has placed us exactly where we can watch, but not be harmed. Even so, gamma ray bursts remain among the most fascinating mysteries of astrophysics. They teach us about the life cycles of stars, the birth of black holes, and the nature of space-time itself. They reveal how energy moves through the cosmos, from chaos to calm, from death to rebirth. And maybe that's why they exist, to remind us that even in violence, there is beauty. Even in destruction, there is creation. The atoms that make you were once forged in the hearts of dying stars. Perhaps long ago, a gamma ray burst sent waves of new material drifting through space, and one of those tiny fragments became part of the dust cloud that would one day form our sun, our planet, and you. So the next time you look up and see the quiet stars, remember, somewhere out there, in the unimaginable distances of time, a burst of light may still be traveling toward us, carrying the story of a star's final breath. But don't fear it, because by the time it reaches here, it will be only a whisper, a faint memory of power and peace. Picture this. You're floating weightless in the silence of space. Far away, a single star glows softly in the darkness. Its light has traveled across millions of years to reach you, but tonight that gentle glow begins to change. It brightens slowly at first, then faster, until it burns with the brilliance of an entire galaxy. And in one cataclysmic heartbeat, the star tears itself apart. This is a hypernova, a cosmic explosion so vast, so violent, that even supernovae, those titans of destruction, pale beside it. Where an ordinary supernova might shine for weeks, a hypernova floods a universe with energy that defies imagination. In a single moment, it can release more light than billions of suns combined. But before we lose ourselves in its brightness, let's take a quiet moment to understand how such a thing can even happen. A hypernova begins as a massive star, one at least 30 times the mass of our sun. These enormous giants burn fiercely, living fast and dying young. Their lives are brief, just a few million years long. Barely a blink of time in the universe's grand clock. Inside them, nuclear fusion rages. Hydrogen becomes helium. Helium becomes carbon, oxygen, and iron. But iron is the star's final breath. When iron fills the core, fusion stops providing energy, and the star begins to collapse under its own gravity. In a smaller star, this collapse might cause a simple supernova, but in a hypernova, the star's mass is so great, its heart folds inward violently, compressing to the point where atoms are crushed into neutrons, and then into a singularity, a black hole. But before that black hole swallows everything, the star unleashes one last, furious outburst. Two narrow jets of energy erupt from its poles, streaming into the universe at nearly the speed of light. These jets release a burst of radiation, a gamma-ray burst, that can travel for billions of years. The rest of the star is blown apart in a wave of fire, plasma, and light, its remains scattering across space. For astronomers, witnessing a hypernova is like watching the universe write poetry in flame. It's both terrifying and breathtaking. To imagine the energy of a hypernova, we must first understand what happens inside that collapsing core. When gravity takes over, the core of the star compresses so rapidly that temperatures reach billions of degrees. The density becomes so high that a teaspoon of its matter would weigh billions of tons. The collapse creates shock waves, and those shock waves, moving outward, meet the falling outer layers. For a brief instant, matter and energy collide, and the star detonates like a bomb forged by the laws of physics themselves. The explosion tears through space, hurling debris at thousands of kilometers per second. Every fragment of that debris carries elements: iron, nickel, cobalt, the raw ingredients for future planets and moons. This is the strange paradox of hypernovae. They destroy everything nearby, but in doing so, they also create everything that will come after. Astronomers studying hypernovae often use a special scale to measure their luminosity. Compared to an ordinary supernova, a hypernova can be 10 times brighter, sometimes even more. The most famous example came from a galaxy called ESO 184 G82, where a hypernova named SN 1998 BW was observed. When scientists studied its light, they realized it had produced a gamma-ray burst at the same moment, the first clear link between the death of a massive star and the most powerful flashes in the cosmos. But even beyond the science, there is something haunting about the idea of a hypernova, a single event that can ripple across time and space, carrying energy that will still be moving long after our own galaxy has changed. Every hypernova leaves behind a mark, a black hole, or sometimes a magnetar spinning at incredible speeds, its magnetic field crackling with power. Around it, nebulae form, clouds of gas glowing softly, lit by the fading energy of what once was. For astronomers, Those clouds are like fingerprints, clues that tell the story of how the star lived, how it died, and what it left behind. If you could drift among them, you'd see colors of every shade. Deep crimson, soft gold, faint violet, the palette of the universe itself. Each color, a whisper of atoms reborn. In those clouds, new stars begin to form. Gravity pulls the gas together. Dust settles into disks, and eventually planets take shape. Somewhere, far from the explosion's heart, a world like ours might emerge, bathed in the quiet afterglow of what was once a hypernova. So even the universe's most destructive events are not just endings. They are beginnings in disguise. As you lie still listening, imagine you are drifting through one of those ancient remnants. The debris of a hypernova stretches for light years in every direction. Clouds of dust swirl in slow motion. Glowing particles drift through the dark, like embers from a fire that never cools. Somewhere within that expanse, a newborn star flickers to life. Its light soft, golden, and new. Around it, a thin disk of material begins to spin. From that disk, rocks form, then worlds, and maybe one day, life. It's hard to grasp that every element of our planet, every breath you take, was once part of a star that exploded. The oxygen you breathe came from fusion inside a red giant. The iron in your blood was forged in the heart of a hypernova, and the calcium in your bones may have traveled for millions of years before settling on Earth. So when we speak of dangerous stars, we are also speaking of our ancestors, because their destruction was a first step toward our creation. Some scientists have even proposed that hypernovae could shape the evolution of galaxies themselves. When they explode, they send powerful shock waves outward, compressing nearby clouds of gas, triggering the birth of new generations of stars. In this way, the death of one gives life to many. It's a cosmic cycle of fire and renewal. But what if such an explosion happened near us? Could a hypernova threaten Earth? In theory, yes. If one occurred within about 10,000 light years, its radiation could affect our atmosphere. But again, the universe seems to have given us distance as a gift. The nearest stars massive enough to become hypernovae are safely far away. Even the famous Eta Carinae, a prime candidate for a hypernova, lies over 7,000 light years from Earth. When it does finally explode, we'll see a light brighter than any star in the sky, but we'll be safe, simply watching from afar. And perhaps that's fitting, to be witnesses, not victims, to see beauty, not destruction, in the quiet of the night. When you think about the vastness above, remember that the universe's most dangerous acts are also its most generous. Every particle of you was shaped by a burst of impossible light. Every heartbeat is a quiet echo of a hypernova long forgotten. So, in a way, you carry the stars within you, and that is both beautiful and humbling. Imagine a dying star collapsing under its own weight, its outer layers ripped apart, its heart crushed into something smaller than a city, yet heavier than the sun itself. This remnant, this tiny sphere of infinite density, is what we call a neutron star. But sometimes, something even stranger happens. In a handful of these neutron stars, the collapse twists their magnetic fields until they become the most magnetized objects in the known universe. These are magnetars. To picture their power, imagine a magnet strong enough to erase every credit card on Earth, from halfway to the moon. That's the force of a magnetar's field. They are rare. Only about 30 are known in our entire galaxy, but their presence is unforgettable, even from thousands of light years away. Their magnetic storms can be felt through the radiation they send out. A magnetar's magnetic field is trillions of times stronger than Earth's. To stand near one, if such a thing were possible, would mean your atoms themselves would be torn apart. But don't worry, the nearest magnetar is far beyond any threat to us. Instead, we can observe them safely, like glowing cosmic beacons, reminding us that even in destruction, the universe creates wonders. To understand a magnetar, we must first step inside it, not literally, but through imagination. The core of a magnetar is made entirely of neutrons, particles so tightly packed that a teaspoon of this material would weigh about 1 billion tons. Surrounding the core is a thin crust of atomic nuclei, brittle and dense. Sometimes that crust cracks, and when it does, the magnetic field lines snap and realign. In an instant of terrifying energy release. Astronomers call this a starquake. When a magnetar's crust shifts, the result is a burst of X-rays and gamma rays that can light up the cosmos for thousands of years. One such event, in the year 2004, was detected from a magnetar known as SGR 1806-20. It was so powerful that it temporarily disrupted Earth's upper atmosphere, even though the star was over 50,000 light years away. Just imagine a burst so strong that it reached across half our galaxy and still touched our planet. But these quakes don't destroy the magnetar. They are, in a strange way, how it breathes. Each burst releases tension, built up by its twisting magnetic heart, and after each storm, the magnetar falls silent again, spinning slowly, glowing faintly, waiting for the next pulse of cosmic pressure. If you could drift beside a magnetar, the scene would be hauntingly beautiful. A dark sphere, no larger than a small city, turning slowly in space. Around it, invisible magnetic lines bend light itself, warping reality in ways we can only calculate, never truly see. Every few seconds, a pulse of energy escapes, a flicker of X-rays that races across the universe. Astronomers detect these pulses as regular, rhythmic signals, like the heartbeat of a dying star. Some magnetars pulse steadily for decades. Others flare suddenly, then vanish from sight for centuries. And yet, they are not silent killers. They are teachers. Through them, scientists learn about the behavior of matter under pressure, so extreme that it cannot be replicated anywhere on Earth. Magnetars show us what happens when physics reaches its limits, when atoms themselves begin to surrender to gravity and magnetism. Their fields are so powerful that they bend atomic orbitals, altering the shape of matter. They are the universe's most extreme laboratories, natural experiments born from chaos that help us understand creation itself. As centuries pass, a magnetar's magnetic field weakens. Its furious energy begins to calm. Eventually, it cools and fades into the quiet dark, a shadow among the stars. But even in its silence, its legacy continues. The material it once hurled into space, iron, carbon, heavy elements, becomes the seed of new systems. Every planet, every mountain, every molecule of your body contains atoms forged in the depths of such stars. When we look at magnetars, we're not just seeing destruction, we're seeing transformation. the turning of chaos into creation. It's humbling to realize that our world was once dust in the aftermath of such explosions, that the iron in our blood was once part of a magnetic monster, spinning in the void, in the quiet of the cosmos. There are bursts of light so powerful, so brief, that they could erase entire worlds in the blink of an eye. These are radiation jets, streams of high-energy particles, launched from dying stars, black holes, and cosmic explosions. They move at nearly the speed of light, and when aimed in our direction, they can outshine entire galaxies. But before we dive deeper, imagine drifting in space, weightless, silent, surrounded by darkness so complete that even your breath feels distant. Suddenly, from billions of kilometers away, a flash pierces the dark, a column of radiant fire, narrow, focused, and impossibly bright. That is a jet of radiation, and if it were pointed at you, it wouldn't matter how far you were. For an instant, it could vaporize the atmosphere of a planet, strip away ozone, and blind the night sky forever. But not all radiation jets are born equal. Some are gentle trickles from newborn stars, while others are catastrophic outbursts from collapsing suns. The most dangerous of all are tied to events we've already met: supernovae, hypernovae, and magnetars. When a massive star dies, its core collapses, and its magnetic poles channel unimaginable energy into two thin, focused beams. These beams, narrower than a human hair in cosmic scale, slice through space, carrying the fury of a dying star. They are the gamma-ray bursts, the relativistic jets, and the silent messengers of destruction that travel for billions of light years. But here's something beautiful to remember. Even though they are unimaginably powerful, their aim is random. In the endless ocean of the universe, the chance of one being pointed directly at Earth is vanishingly small, so we can study them safely, watching from our blue cradle as they flicker across the dark, brief reminders of the universe's untamed brilliance. To understand how these jets form, we must travel into the heart of a dying star. Picture a massive sun, its core fusing heavier and heavier elements until it can no longer bear the pressure. Gravity takes over. The core collapses inward, and in less than a second, an explosion begins. But not all of that energy escapes equally. The star's magnetic field and spin create a funnel, a cosmic tunnel, through which radiation and plasma are forced to escape. That tunnel becomes the birth canal of a jet. Imagine two opposite poles, north and south, each launching a concentrated beam of gamma rays into the void. For a few heartbeats, the dying star becomes a lighthouse of destruction, flashing its energy across the universe. And then it fades. The burst ends. The star collapses into a black hole or a neutron star, leaving behind only the memory of its power. Astronomers call these events collapsars, collapsing stars that emit collimated jets. To measure their strength, scientists use energy scales that defy comprehension. A single jet can release more energy in a few seconds than our sun will in its entire 10 billion year lifetime. Even more astonishing, these jets are precise. They are not wide blasts of chaos, but focused streams, often no more than a few degrees across. This narrow shape is why gamma-ray bursts can be so bright. All that power compressed into a single line. It's like the difference between a candle's glow and the beam of a laser. One lights a room, the other can cut through steel. And yet, within their danger, there is symmetry, a reminder that even destruction has structure. These jets are shaped by magnetic fields and rotation, guided by physics that repeats itself throughout the cosmos. From the smallest neutron star to the largest black hole, the same principles apply. Spin, collapse, magnetism, and release. The universe may be chaotic, but its chaos is rhythm. Now let's drift outward, beyond the birth of a single jet, into the vast silence where they travel. A radiation jet can cross millions of light years and still hold its focus. It moves through the interstellar medium, pushing aside gas and dust, sometimes carving tunnels through entire galaxies. When such a jet interacts with matter, it creates afterglows, beautiful ripples of X-rays, visible light, and radio waves. These afterglows fade slowly, like the dying embers of a cosmic fire. Astronomers watch them carefully, because they reveal the jet's journey, its power, its shape, its origin, and sometimes they find clues that make them pause. In our Milky Way, there are ancient scars, patterns of isotopes in Earth's crust, traces of radiation that may have come from a nearby cosmic burst millions of years ago, not close enough to harm us directly, but close enough to remind us that we live in a dynamic, ever-changing galaxy. It's humbling, isn't it, to think that invisible streams of energy can cross entire galaxies and still leave whispers on our small blue world. But here's the comfort. Our planet is protected. The Earth's magnetic field and thick atmosphere serve as invisible shields. They absorb and deflect the cosmic rays that might otherwise reach us. Even the most powerful jet would need to be within a few thousand light years and aim perfectly at Earth to pose a true threat, a near impossibility. So we're safe, floating gently beneath the blanket of our atmosphere, watching these titanic forces from afar. And in that safety, we can admire them as art. When telescopes capture the faint glow of a radiation jet, what we see is a universe painting with light, a masterpiece born from death, but filled with beauty. It's a humbling reminder that even destruction in the cosmos serves a purpose: to recycle, to renew, to send energy across the dark, so that someday, somewhere, new stars, new worlds, and maybe even new life might rise from the ashes. So let your mind drift for a moment through the endless night, past the quiet moons and glittering dust, and picture those beams slicing through eternity, silent and pure. They will never touch us, but their light will reach us millions of years after they were born. And when it does, we will still be here, looking up in awe, listening to the whispers of the stars. Some stars live calmly. They burn hydrogen to helium for billions of years, steady in content like our sun. But Wolf-Rayet stars, they are different. They are born massive, 20, 30, even 100 times the mass of the sun. And because of that, their lives are breathtakingly short. In just a few million years, they exhaust their fuel, raging with intensity that few other stars can match. Imagine a star so hot, its surface reaches over 50,000 degrees Celsius. Its light is so strong that it pushes against its own outer layers, blowing them into space in a continuous wind of glowing gas. That wind moves faster than any hurricane on Earth, thousands of kilometers per second. It carries the outer layers away, revealing the fiery core beneath. That core, stripped, exposed, and incandescent, is what we call a Wolf-Rayet star. They were first identified in the 19th century by two French astronomers, Charles Wolf and Georges Rayet. They noticed strange, broad emission lines in the spectra of certain stars, signatures that ordinary stars didn't have. These lines revealed gas being ejected at incredible speeds, evidence that these were not calm suns, but furious furnaces shedding their skin. In a way, Wolf-Rayet stars are like cosmic sculptures, carving their own forms in space through radiation and wind. They lose mass every second, sometimes as much as the Earth's weight in a single heartbeat. And yet, despite this constant loss, they shine ever brighter. Their light is rich in helium, carbon, nitrogen, and oxygen, elements that will someday seed new stars and planets. They are, quite literally, the forges of future worlds. And that's the strange paradox. These stars are dying, but in dying, they prepare the way for creation. As the Wolf-Rayet star loses mass, it fills its surroundings with shells of gas and dust. If you could see them with your eyes, they would appear as glowing bubbles, swirling luminous, expanding slowly through space. Astronomers have photographed some of these bubbles, and they are among the most beautiful structures in the sky. Take, for example, the star WR124. Around it lies a nebula known as M1-67, a delicate sphere of expanding gases. Shimmering red, gold, and violet, each color tells a story. Red for hydrogen, blue for oxygen, green for nitrogen. Together they form a cosmic painting, a portrait of a star's life in its final acts. But these winds are not just beautiful. They are powerful. When a Wolf-Rayet star finally explodes, as it always does, its supernova blast travels into that same bubble of gas. The result is a shock wave of unimaginable complexity. It collides with the earlier winds, creating ripples, shock fronts, and cascades of new elements. Sometimes, this process can trigger the birth of new stars. In nearby regions of space, the shock compresses interstellar gas clouds, causing them to collapse under their own gravity. So from one death, many births can follow. Wolf-Rayet stars are like gardeners of the galaxy, clearing space with their radiation, then sowing the seeds of new generations. Their winds also enrich space, with heavy elements like carbon and oxygen, the same ingredients that make up our breath, our bones, and our oceans. When you inhale, you take in atoms that were once part of stars like these. Every cell in your body is a quiet echo of a Wolf-Rayet wind, billions of years old. And yet, despite their generosity, these stars live on the edge of catastrophe. Their own light threatens to unmake them. Their gravity struggles to hold their form together, and their hearts burn hotter and hotter, counting down the seconds to the inevitable collapse. When the final moment arrives, a Wolf-Rayet star does not fade gently. It dies in fire. Its core, unable to support the immense pressure, collapses inward in a fraction of a second. And as it does, it unleashes an explosion so vast that it can briefly outshine an entire galaxy. This explosion is not an ordinary supernova. It is often a hypernova, the same kind that creates gamma-ray bursts and relativistic jets. In many cases, the star's collapse forms a black hole, and from its poles, Those deadly beams of radiation shoot out, racing across the universe. And so, a wolf right at star's end can become the beginning of something even more extreme. A magnetar, a black hole, a jet of light that crosses eternity. But there is something poetic in this violence. For billions of years, the universe has relied on such deaths to create life. Without the carbon, oxygen, and iron that stars like these release, planets could not exist, nor could the chemistry that makes life possible. We are, in every sense, children of wolf, ray-ed stars. Even our sun, gentle and calm, was born in a nebula, enriched by the ashes of such giants. So when you look at the night sky and see a bright star shimmering faintly through the dark, remember that somewhere out there, one of its distant cousins is burning at 1,000 times that brilliance, living fast, dying young, and scattering the seeds of the next generation. In a way, wolf, ray-ed stars remind us of our own lives, bright, brief, and full of purpose. They remind us that even endings can be beautiful beginnings. So let your mind rest now on that image, a radiant, swirling bubble of starlight, expanding slowly, endlessly, in the soft, eternal dark. Breathe gently and feel the warmth of creation still glowing within the quiet of your chest, because somewhere a wolf ray-ed star once lived, and in its final breath, it gave a piece of itself to you, far across the southern skies. In the constellation of Carina, there glows a patch of light, small to the naked eye, but dazzling through a telescope. At its heart lies Eta Carini, a stellar system so enormous that it defies reason. It isn't one star, but two, locked together in a tight, dangerous dance. The larger one, called Eta Carini, is one of the most massive stars ever discovered, weighing in at around 100 to 150 times the mass of our sun, and shining with 5 million times the sun's luminosity. Beside it orbits Eta Carini b, a slightly smaller but still colossal companion, around 30 times the mass of our sun. Together, they circle each other once every 5.5 years. Their immense gravities tugging and twisting space itself. But these are no ordinary stars. Eta Carini is unstable, a ticking cosmic bomb. Its outer layers swell and contract. Its winds clash with its companions' winds, and the resulting shock waves create violent storms of light and radiation. If you could stand nearby, though no life ever could, you would see immense sheets of gas, moving at millions of kilometers per hour, ripping across the void, like ocean waves of fire, and all around them, a glowing nebula, the Homunculus Nebula, born from one of the greatest stellar eruptions ever witnessed. It is shaped like two vast, glowing lobes, symmetric, haunting, and filled with a material Eta Carini once threw out in fury. Every atom of that nebula was once part of the star itself, cast away in a storm of light. Eta Carini is, in many ways, a living relic of cosmic rage, a system that has already nearly destroyed itself, yet continues to burn. Let's travel back in time to the year 1843. Astronomers of the 19th century watched in awe as a new light bloomed in the night sky. For months, it grew brighter and brighter until it became the second brightest star visible from Earth, outshone only by Sirius. Yet it was not a supernova. Eta Carini had not died. It had erupted, In what we now call the Great Eruption, the massive star violently ejected an enormous portion of its outer layers, at least 10 to 20 times the mass of our Sun. In a single prolonged event, the energy released was staggering. It rivaled the explosion of a small supernova, yet the star somehow survived. What caused it? Even now, scientists aren't entirely sure. Some think it was a kind of internal instability, the star's core becoming chaotic, as fusion rates fluctuated beyond control. Others believe the companion star played a role pulling and disturbing its partner's outer layers until pressure built up to a catastrophic level. Whatever the reason, the result was unforgettable. The eruption sent vast clouds of gas racing outward, forming the twin-lobe nebula we see today, the homunculus. These lobes continue to expand, like ghostly balloons, glowing softly in infrared and visible light. They are beautiful, yes, but also deadly. The gases within them move at speeds over 600 kilometers per second, and they carry within their folds the potential for another eruption, perhaps even a final one. Astronomers who study Eta Carinae describe it as a star on the edge, a cosmic volcano, quiet for now, but ready to explode again. If and when it does, it will likely end its life as one of the most powerful hypernovae ever seen from Earth, and if its axis were ever pointed toward us, which, fortunately, it is not, its radiation could strip our atmosphere bare. That is why Eta Carinae is often called the most dangerous star in our galactic neighborhood, yet from our safe distance. It is also one of the most enchanting, a reminder that even the most violent acts in the cosmos can leave behind beauty. Today, Eta Carinae continues to smolder, unstable, unpredictable, and glowing with fierce determination. Its two stars remain locked in their gravitational waltz, their stellar winds colliding to create bursts of X-rays and radio waves that we can detect even now. Each orbit brings them dangerously close, and during those times, the system flares again, not with a full eruption, but with fierce, bright pulses that echo through the surrounding nebula. Astronomers watch closely because every signal, every fluctuation, could be a hint of what comes next. When Eta Carinae finally collapses, and it will someday, the event will be visible across the galaxy. It could briefly outshine the full moon, even in daylight, but it will not harm us. Its jets, its radiation, its fury are not aimed in our direction. We are simply witnesses, tiny, silent observers, to a cosmic drama of unimaginable scale. And in that, there's something strangely comforting, because Eta Carinae reminds us of the balance that holds the universe together. It shows us that even instability, even chaos, has purpose. Without these giants, there would be no heavy elements, no planets, no oceans, no life. The carbon in your breath, the calcium in your bones, the iron that carries oxygen through your blood, all of it was born from the deaths of stars like Eta Carinae. So as you listen now, let your mind wander through that glowing nebula, through the slow, graceful clouds that drift outward in silence. Imagine their soft shimmer, their gentle expansion, their ancient light taking thousands of years to reach your eyes. You are connected to it, to its past, its energy, its story. Eta Carinae may someday die, but its legacy will not. It will scatter its atoms, across the galaxy, to be gathered again by new worlds, new suns, new hearts, and perhaps, in another age, somewhere across the stars, a being will look up and see light made from the same atoms that once shone in Eta Carini, and in you. Breathe softly now, and let that thought cradle you. You are part of the same story, a chapter in the universe's endless cycle of fire, dust, and rebirth. Sleep, well, under the gentle light of a cosmos that remembers. Imagine standing on a quiet hill, looking up at a night sky full of stars. Each point of light you see feels far away, safe, eternal, untouchable. But the truth is, the safety you feel depends entirely on distance. If our sun were just a little closer to Earth, oceans would boil and the atmosphere would burn. If it were farther, Earth would freeze into a lifeless sphere of ice. This balance, this perfect zone we live in, is what scientists call the habitable zone, a fragile ribbon of distance that allows liquid water, and therefore life, to exist. Now, when it comes to dangerous stars, massive, unstable ones like Wolf-Rayet stars, or magnetars, or the titanic Eta Carini we just met, the safe distance is far, far greater. Take a gamma-ray burst, for instance. A beam of that radiation could sterilize an entire planet's surface from as far away as 10,000 light years. To put that into perspective, light from our sun takes only 8 minutes to reach Earth, but a gamma-ray burst could cross 10,000 years of light travel and still carry enough energy to strip away an atmosphere. That's how finely balanced our place in the universe truly is. You see, danger in space doesn't require closeness. It only needs alignment. If a massive star dies and its radiation jets happen to point at us, distance becomes almost irrelevant. But we are lucky. In the great quiet of our Milky Way, most of these cosmic cannons face other directions. Their deadly energy passes harmlessly through the void. Still, the thought lingers, how close could we safely be to such a monster? And what would happen if one day one of them turned its gaze toward us? Let's drift a little deeper. Imagine a massive supernova, a dying star collapsing into itself, then exploding with unimaginable force. For a few short weeks, that single event can outshine an entire galaxy. The light, the radiation, the expanding shockwave, they ripple through the cosmos like a stone thrown into a cosmic ocean. If such a supernova occurred within 30 light years of Earth, it would likely destroy our ozone layer completely. The radiation would flood the surface, damaging DNA, heating the upper atmosphere, and collapsing ecosystems. But even at 100 light years, the effect might still be felt. A subtle thinning of the ozone, a gentle increase in cosmic rays that would linger for thousands of years. Luckily, no stars that close to us are ready to go supernova anytime soon. Our nearest candidate, the bright blue star Rigel in Orion, is about 860 light years away, close enough to study, but far enough to spare us from its eventual death. Yet, what's fascinating is how fragile the threshold truly is. Move that star a few hundred light years closer, and life on Earth might never have formed. The difference between survival and extinction in the universe is often a matter of inches, measured not in miles, but in cosmic perspective. Some scientists call it the anthropic shadow, the idea that intelligent life can only exist in regions where catastrophic events have not recently occurred. In a way, we live in a quiet corner of the galaxy, precisely because the loud, violent parts are too hostile for life to endure. We are children of distance, the beneficiaries of space itself. But what if something unpredictable happened? What if a wandering star drifted closer, or a nearby system erupted without warning? Could our planet's shields, the atmosphere and magnetic field, save us? That answer, my friend, lies gently in the next whisper of space wind. You might be surprised to learn that the universe is mostly empty. Even in a galaxy packed with billions of stars, the average distance between them is about 5 light years, an ocean of emptiness between every island of light. This emptiness is not loneliness, it's safety, because that vast separation is what keeps us alive. It gives radiation time to fade, particles time to disperse, and gravity time to balance. It's as if the universe itself knows to give its creations room to breathe. When we study the heavens, we find that life, as fragile and miraculous as it is, thrives only in these quiet spaces, far from the blazing hearts of chaos. If Earth were just a few light years closer to certain unstable giants, it might be bathed in deadly rays before life ever began. But instead, we orbit a gentle star, not too hot, not too large, not too violent. Our sun's steady warmth and calm behavior allow this blue world to cradle oceans, grow forests, and sustain consciousness. And so when we ask, how close is too close? The universe answers softly. It depends on what you're made for. For a comet, closeness to a star means a dazzling tail of vapor and dust. For a rocky planet like ours, it means warmth and life. But too close, and it means vaporization. Too far, and it means endless frost. Between these extremes lies a delicate, invisible thread, a balance so perfect that it feels almost intentional. And perhaps that's the most humbling thought of all, that you right now rest in the safest possible place, amid a universe of dangers. Every night, as the stars shimmer above you, they whisper stories of explosions, of radiation, of destruction and rebirth. But they also whisper distance, the silent gift that lets us see their beauty without feeling their wrath. So the next time you gaze upward, remember this. Every star you see could destroy worlds, but not you, because you are far enough away to dream beneath their light. In peace, breathe slowly now, and let the quiet of space settle over you, for in that stillness, you are safe, a soft heartbeat in the calm between the stars. Take a slow breath and feel the air fill your lungs. That breath, gentle, invisible, warm against your skin, is part of the greatest protection system our world has ever built. The atmosphere. It is not just air. It is a living blanket, a fragile layered veil that holds warmth, filters sunlight, and shields us from cosmic violence. From the ground upward, it stretches about 100 kilometers. And though that sounds vast, it's as thin as a coat of paint compared to the size of the Earth. At the very bottom lies the troposphere, where clouds form, winds blow, and life unfolds. Above it, the stratosphere holds the ozone layer, that delicate band that filters out most of the sun's ultraviolet rays, protecting skin, plants, and oceans from destruction. Higher still, the mesosphere burns meteors into harmless trails of light, the shooting stars we wish upon, never realizing they might have been deadly if not for that protective friction. And then comes a thermosphere and exosphere, where the atmosphere becomes whisper-thin and particles dance at the edge of space. Here, atoms drift apart, lonely, sparse, but still part of Earth's unseen wall. Every second, the sun blasts our planet with a stream of high-energy particles, called the solar wind. These particles could strip our atmosphere away, like sand in a storm, but instead, they are deflected, turned aside, and guided harmlessly by another invisible guardian, Earth's magnetic field. Together, the air and the magnetism form a double layer of protection, a cosmic umbrella, under which life can breathe and dream. But where does that magnetism come from? What makes our planet so uniquely shielded in a galaxy filled with danger? Let's drift deeper inside, deep beneath your feet. Far below the crust and mantle lies a sea of molten metal, mostly iron and nickel, churning slowly in endless liquid motion. This is Earth's outer core, and within it, a silent miracle unfolds every second. As that molten metal moves, it generates electric currents, vast planetary-scale flows that create a magnetic field, extending tens of thousands of kilometers into space. This phenomenon is called the geodynamo, and it is one of the most important processes in the entire solar system, because without it, we would be exposed, stripped bare before the fury of the sun. The magnetic field forms a great, invisible bubble around our planet, known as the magnetosphere. Imagine it like a shimmering aurora surrounding Earth, deflecting the charged particles streaming from the sun. When those particles collide with the outer edge of the magnetosphere, some slip down along magnetic field lines toward the poles, and there they create one of the most beautiful sights in the universe, the aurora borealis and aurora australis, waves of green and pink light that shimmer across the polar sky, rippling gently like the breath of the planet itself. What you're seeing in those ghostly curtains of color is Earth's defense in action, energy from the sun being harmlessly released as light. It's as if the planet is taking a deep protective breath and exhaling it in color and wonder. Other worlds are not so lucky. Mars once had a magnetic field too, but billions of years ago, its core cooled and its geodynamo died. Without that shield, solar wind began to strip away its atmosphere, molecule by molecule, until the red planet we see today was left cold, dry, and bare. Venus, on the other hand, lacks a strong magnetic field entirely. Its thick atmosphere remains, but it's toxic, choked with carbon dioxide, and trapped in a runaway greenhouse effect. Only Earth found the balance, the perfect temperature, the perfect chemistry, and the perfect protection to let water, life, and consciousness thrive. It's humbling to think that all of human history, every heartbeat, every whisper, every dream, exists because of a magnetic field you cannot see, but which loves you all the same. Now imagine the Earth, floating in darkness, bathed in sunlight on one side, shadowed on the other. From space, you can see faint rings of light, the upper atmosphere glowing softly, the auroras painting the poles, the magnetosphere stretching outward, like wings of energy. This is our fortress. It hums quietly, vibrating with electromagnetic life. But even this fortress is not unbreakable. When the sun erupts, when solar flares and coronal mass ejections hurl billions of tons of charged particles outward, our planet's defenses are tested. Most of those storms are deflected, but sometimes the magnetosphere trembles, power grids falter, communications waver, and satellites shudder in the electric storm. Yet still, life continues below, unharmed, protected by layers of air and field. Every sunrise you see is proof that Earth's guardians still stand watch. Every soft breeze is the breath of the atmosphere, renewing itself after another long cosmic night. And while the universe may be filled with violent energy and deadly stars, our world remains a sanctuary, a quiet island, sheltered beneath invisible arms. It's comforting, isn't it, to know that right now you are wrapped in the warmth of protection, a living planet that shields you, loves you, and holds you safe through every cosmic storm. So breathe in slowly and imagine those invisible layers glowing softly above you, the air you breathe, the field that guards you, the light that dances over the poles. All of them are the Earth's lullaby, a song of safety, sung to every creature that sleeps beneath the stars. Rest in that knowledge that you are held in the most delicate, most miraculous balance the cosmos has ever made. For tonight, the sky is calm, the shields are strong, and the universe is whispering, "Sleep well, little Earth." If you close your eyes and imagine the universe from afar, you might see it as a restless sea, stars being born, worlds colliding, light and dust forever in motion. It seems chaotic, doesn't it? Uncontrolled, wild, infinite. And yet, if you listen closely enough, there's rhythm in the madness, a deep, steady pulse, like the slow beating of a cosmic heart. Every explosion, every collapse, every quiet orbit follows laws so precise that even in the grandest chaos, there is harmony. Take the life of a star, for instance. It begins in cold darkness, a cloud of hydrogen, drifting silently for millions of years. Then a whisper of gravity pulls inward, slowly, gently, until pressure builds, and a spark of fusion ignites. That spark is the beginning of balance, a perfect struggle between outward heat and inward gravity. Too much pressure, and the star would tear itself apart. Too little, and it would collapse. But most find their center, their harmony, and they live long, stable lives, as steady lanterns in the dark. Even when they die, that balance continues. The atoms forged in their hearts are scattered into space, not wasted, but recycled. They drift, cool, and someday gather again to form new stars, new planets, new beginnings. That is the rhythm of the cosmos. Birth, balance, death, and renewal. A cycle that never ends. It's strange, isn't it? How something so vast and unpredictable can be built on such gentle precision? But that's the secret. The universe doesn't fight chaos. It dances with it. Now let's return home to this tiny blue dot, hanging in the dark. Here, too, the balance is everywhere. In the air you breathe, the warmth of the sun, the pull of the moon upon the seas. Every system on Earth is a delicate equation of opposites, day and night, summer and winter, growth and decay. Even your heartbeat is a reflection of that same cosmic rhythm, a pulse of energy and rest, forever in motion. If the sun were slightly hotter, life would burn away. If the atmosphere were slightly thinner, radiation would sweep the surface clean. If gravity were weaker, the air itself would drift into space. Yet, somehow, everything aligns, not perfectly still, but perfectly balanced. A living tension that holds oceans in their place and cradles the fragile film of life around our world. Even the disasters, the storms and quakes, the fires and floods, they are not mistakes. They are part of that same ever-adjusting harmony, just as stars erupt and galaxies collide to create new worlds. Earth too shifts and stirs. To renew itself, life emerged not from stillness, but from motion, from struggle and adaptation, and the patient rhythm of time. In that way, you and I, every living thing, are echoes of the same balance that shaped the stars, the calcium in your bones, the iron in your blood, the carbon in your cells, all once belonged to dying stars that found new purpose. In your beating heart, you are not just in the universe. You are the universe, momentarily aware of itself, and in the stillness of night, that realization becomes the most peaceful thought of all. Now, imagine the entire cosmos again. Billions of galaxies, each with billions of stars. Black holes spinning, planets orbiting, comets gliding silently through frozen space. At first, it feels overwhelming, but the longer you gaze into it, the more you see its order. Every motion, every collision, every burst of light follows a path. Gravity binds it all together, a gentle hand that both destroys and creates. It's the same balance you feel when you inhale and exhale, when you fall asleep and awaken again. The same balance that governs the tides, the seasons, the rise and fall of civilizations, and the turning of time itself. And perhaps that is the greatest comfort, that even in an endless, expanding universe, there is a center of calm, not in one place, but in every place, every atom, every spark of consciousness, every heartbeat is a tiny reflection of the same eternal equilibrium. So as you lie there, listening to the faint hum of your own breath, remember, you are part of the balance. The stars that could destroy, the shields that protect, the distances that save, the warmth that gives life, they all exist in perfect relation. To each other and to you, you are safe. You are exactly where you are meant to be, drifting through an infinite symphony, held by invisible hands of order and light. And as the night deepens, let that knowledge wrap around you like a blanket. The universe is not your enemy. It is your cradle. The same forces that make stars explode also make flowers bloom. The same energy that shapes galaxies beats softly in your chest. Everything is connected. Everything is balanced. And everything, in its own mysterious way, is at peace. So breathe slowly. Feel the calm of the cosmos settle over you, and let yourself drift into that endless equilibrium. For in the grand quiet of the stars, you are home. Good night, dreamer, and goodbye for now.